Hello students, today we are going to discuss about Unit 4 Digital Modulation Schemes. The course outcome of Unit 4 is analyze the spectral characteristics and bit error rate performance of digital modulation techniques. So we are going to discuss about what is quadrature amplitude shift keying. In the previous class we discussed about QPSK, BFSK, BPSK. The difference between QPSK and quadrature amplitude shift keying is nothing but here the amplitude as well as phase are going to be modified with respect to the input symbols. That is, in phase shift keying, phase of the carrier is going to be modulated, whereas amplitude is kept constant. In FSK, frequency of the carrier is going to be modified by maintaining the amplitude levels as constant. In quadrature amplitude shift keying, two schemes are merged and introduced as quadrature amplitude shift keying or QAM, quadrature amplitude modulation. The amplitude of the carrier as well as phase are going to be modified. So that is the major difference. So by doing this, we can improve the transmission bandwidth and also bit error rate is reduced. So the QPSK system has signal points present at the circumference of signal space representation diagram. If amplitude of the signal is also varied, then the points may lie inside the diagram. As both amplitude and phase are varied, it is called as quadrature amplitude phase shift keying. So this is a geometric signal representation of QASK, and the Euclidean distance constellation of QSK are given in this diagram. So as I told, amplitude as well as phase shift is going to be there. So 2 power 4 combination. So 16 combinations are available in the constellation diagram. So each and every points, this point represents a Euclidean distance or constellation points for different amplitude as well as phase shift values. For 4-bit symbol, the possibility is 16. So distance between neighboring points are considered as 2a. This is a. So between these two points are equivalent to 2a. So the energy of the signal is considered as a is equal to 0.1 EB. Euclidean distance, as I told you, it is equivalent to 2a. So d is equal to a into the magnitude value is 0.1 ES. So 0.4 into ES. Each symbol, 4 bits are required to represent that particular symbol. So we need ES is equal to 4 into EB. So DQPSK, the distance or Euclidean distance to represent this quadrature phase shift keying is equivalent to root of 4 into EB. So this is the block diagram of QSK transmitter. It consists of serial to parallel converter, digital to analog converter, then we have a product modulator and summer. So this is for converting the binary streams into parallel combination of symbols. That is, we are going to modify the phase as well as amplitude. So zeros and ones are the normal bit streams are converted into parallel combinations. So we can represent the bit streams as a symbols with 4 bits starting from BK to BK plus 3. So the upper half is directly given to digital to analog converter, whereas the second block is inverted and it is given to D2A converter. So this is for even numbers and this is for odd number, odd bit stream and even bit stream like PSK. One multiplier is there, so the even streams of input is going to be multiplied with the high frequency carrier signal. For both the case, it is going to be cos 2 pi f naught of t. But in the odd stream, we are introducing sine because we need to introduce 180-degree phase shift. So it is equivalent to sine 2 pi f naught of t. So the sum of these two even and odd combination will produce quadrature amplitude shift keying or quadrature amplitude modulation. So S of t is equal to k1 into a pi 1 of t plus k2 into a pi 2 of t. So pi 1 of t is nothing but coefficient expansion. We already derived this 2 divided by tb cos 2 pi f naught of t. Similarly for the second case, the only change is sine. So sine 2 pi f naught t. The value of a already we determined as 0.1 into a. So S of t is equal to substitute all these values in this equation. We get this equation. So S of t is equal to constant into 0.2 ps cos 2 pi f naught of t plus k2 into 0.2 ps sin 2 pi f naught of t. So k1, k2 are amplitude of modulated signals, that is magnitude, or we can call it as a constant terms. S of t is equal to ae of t ps into cos 2 pi f naught of t. So here we consider odd function, so odd naught of t root ps sin 2 pi f naught of t. So this is QASK transmitter. So receiver, so in the receiver we need to demodulate the original signal, or we need to recover the bit streams. It is similar to PSK. QASK signal are applied to product multiplier along with the high frequency carrier signal. Here we are using one integrated circuits. The only difference is here we introduce D2A in transmitter. So we have to introduce analog to digital converter in the receiver circuit. In transmitter we are using serial to parallel converter, whereas in the receiver we have to convert this parallel combination of bit stream into serial thing. So that is the difference between PSK and QASK. So this is the power spectral density equation for QASK, and the bandwidth of this is equivalent to 2 fp by n, and the probability of error equation is equivalent to 2 into 1 minus 1 divided by root m, or ERFC, error function of EB by n naught. Thank you.